Welcome to definite integrals, which is part 5 of our Calculus 1 review. So just a quick definition. The definite integral from a to b of a function f of x denoted with the integral sign with a subscript a and a superscript b, f of x dx, is the signed area under the curve between the x-axis and the curve. When we first see definite integrals, we were introduced to them geometrically. So finding the definite integral geometrically, we can break our regions into rectangles. So we can use what are called Riemann sums to break the regions or the region into smaller and smaller rectangles or narrower and narrower rectangles. And add up their areas. To find the approximate signed area under the curve. And then we can always take the limit as our rectangles, the width of our rectangle essentially goes to 0 to find the actual area. Or the limit as the number of rectangles goes to infinity. To find the exact definite integral. So, for example, if we wish to find the definite integral from 0 to 1 of x squared dx, right, we know what x squared looks like. And if we wish to find this area under the curve, we could divide the region into a bunch of rectangles. For example, we could start off just splitting into 4 rectangles, each a quarter wide. We can either use the left side of the region for the height, the right side of the region for the height, or the midpoint of the region for the height. So this is using the left-hand Riemann sum. Similarly, we could have done with the right-hand side. Again, breaking up into 4 intervals. We're just looking at 4 rectangles to start off. If we use the right-hand side, we base the height of each rectangle on the right side of its interval. This is our right hand. Riemann sum. So to do these, we would total up the area, and then we can take more and more rectangles, making them narrower and narrower and narrower. So these are with 4 rectangles. Right. To calculate the general area, we do the width times the height. So if we do in general, if we are trying to do a definite integral from a to b of f of x dx with n rectangles, if we want to do the left hand, we're going to take our region from A to B, split that into n rectangles. Right? So the width we'll denote with a delta x is going to be b minus a split over n rectangles. The height will be based off the left-hand side. So the height, we'll have n rectangles. So the height of rectangle I we did based off of, we'll start off at A. So what we'll do is f of xi minus 1, where x0 is A, and xi is A plus I times delta x. So for each new rectangle, we're going to, or for each new value, we'll just add on a copy of delta x to A. And so the height of rectangle I will be f of A plus I minus 1 times delta x. And so the area of rectangle I would be delta x times f of A plus I minus 1 times delta x. And so our sum, our definite integral from A to B of f of x dx is approximately the sum from I equals 1 to n, there's our n rectangles, of delta x times f of A plus I minus 1 times delta x. For the right-hand side, so this was left hand. For the right-hand side, It's the same thing, except the height is based off the right side. So the height this time around will just be f of xi, which is just f of a plus I times delta x. So that slightly changes our area as well. So we get our definite interval from a to b of f of x dx is approximately the sum from I equals 1 to n, or n rectangles, of delta x times f of a plus I times delta x. So these formulas we can run, and then of course we can take the limit as n goes to infinity to get the actual definite integral. In the next video, we will see a much shorter way of taking definite integrals. But this is kind of, and then, as I said, we take the limit as n goes to infinity to find the actual definite integral from a to b, f of x dx. So this is one way we can find our definite integrals. We'll get a shortcut in the next video for at least some cases.